Thank you, everybody. Good afternoon, and thanks a lot for coming on what's really a beautiful afternoon here. It's a pleasure to be here in Piketon. I was last here in 2019. I might have met some of you at the Piketon High School. I talked on August 10th, 2019 here in Piketon and talked about some of the first results I had done. But my first introduction to Piketon came in 2019 when I also talked by telephone at a meeting that was held by Matt Brewster of the Pike County General Health District. I believe it was in Waverly. At any rate, I will make reference to that meeting. But since that April of 2019, I've had a public presence in Piketon, and indeed I have been following the, I'd say, the breadcrumbs of the contamination from the Portsmouth nuclear site. So there's my title, Professor Emeritus. What that means is I'm retired. I don't have a salary, but I have ongoing professional and technical affiliation with the university. And so what I'm doing is a mixture of outreach, community service, and things of my own interest and my own intellectual curiosity, as well as my desire to genuinely help people. And yes, I also do things that earn me some money. For example, I work in a laboratory at NAU, it's called Northern Arizona University, where we analyze plutonium samples for people from around the world, and it's actually a very useful tracer of the Anthropocene age. It shows up in sediments and soils post-1952. It comes from nuclear weapons testing. So when the Department of Energy starts to say, oh, well, this is from nuclear weapons testing, I'm the guy they should talk to about where does it come from. So I do weird things. I'm very interested in elements like uranium and plutonium and so on. And kind of the question is, where do they come from? If I could go to the next slide here. I use the word nuclear forensics to describe what I do. I look at breadcrumbs and how they get dispersed in the environment. I'm interested in questions of origin, so where do things come from? I'm interested in sources, that's where the stuff comes from, and receptors. We use the word receptors to indicate where does this stuff go, and so receptors can be soil or water or biological systems. We could be talking about what's in my hair or what's in my teeth or what's in my bones or in my kidneys. Those are all receptors as well. In my work, I'm interested in all kinds of environmental contamination. As Pat mentioned, I got my start at US EPA about 30 years ago or so. I was in the business of helping the Department of Justice and the US EPA prove where does lead contamination come from near Superfund sources. During that time, I did a lot of work on lead, but in the last couple of decades, it's been more about uranium and plutonium. And I'm interested in former nuclear sites, and at these places, the prevailing question that I'm trying to answer is, how far does the footprint of contamination go? You know, is it a mile? Is it 3 miles? Is it 6 miles? Is it beyond that? And that's an unknown, because if you start scratching the surface, there's not a lot of hard data. Some sites, yes, but many other sites, there's not a lot of hard data. I'd like to think that a lot more light has been shed on the off-site contamination from the Portsmouth nuclear reservation. A lot more light has been shed on things in the last few years as a result of, disclosing data, taking samples on behalf of the public and disclosing data. I start in this work with a standpoint that's called the null hypothesis, and that's a term that comes from statistics, and it basically means, what is your default assumption? It's sort of like, in the criminal justice system, the default assumption is that someone who has been accused of a crime is innocent until proven guilty. Or in civil litigation, the plaintiff has to prove something about the defendant. So my default position when I do this work is we expect to find uranium everywhere. We do. It's in my backyard too. We expect to find it everywhere, but the default assumption or the null hypothesis is that the uranium is from nature. It's coming from nature. It's not coming from something else. We also expect to find small amounts, pretty small amounts of plutonium and neptunium in the Earth's surface. It's not really from nature, although if you want to split hairs about it, you can find a few plutonium-239 atoms and neptunium-237 atoms in uranium ores. But for the most part, these guys can be found on the Earth's surface from 1950s, 1960s nuclear weapons tests. So that's sort of the standpoint that we begin with. And so then I collect samples and I test these samples against those null hypotheses. And the default is always that the contamination is not there until it is proven that it is there. Just like, you know, the innocent are innocent until a convincing case is made otherwise. In my work, I conduct my own field work. I go poking around in the field, taking samples. I do my own lab work, and I also do all my own data interpretation. And so I put all of the elements together, and I'm able to say things like, well, I found this contamination from here, there. So for example, on April 27th, 2019, I said to the community, I found enriched uranium from the Portsmouth nuclear plant in the attic dusts of Zahn's Corner School that were sampled by Elizabeth Lamerson and her husband Josh Lamerson. And, you know, my friends, that coming to that conclusion and making that statement is like calling balls and strikes in the work of an umpire. I am gathering samples, analyzing them, measuring the isotope compositions of these elements against the null hypothesis. And in the case of Zahn's Corner School, I said, well, sure, there's uranium from nature here, but there's an added component. There's other stuff mixed in here that came from the Portsmouth nuclear site. So, with respect to the work we're kind of making, field and lab investigations and gathering together data. I work with citizens and I do some of my own sampling, but I collect samples that enable these null hypotheses to be tested, and we want to test them to learn something about the place like the Portsmouth site. So the primary lab work that I do uses an atom counting instrument. It's called a mass spectrometer. Basically, it measures relative numbers of atoms of uranium or something like that. Plutonium works also, and it gives us the data that we need to evaluate these null hypotheses. If we could go next. So I've already used the term isotope. What do I mean by that? Well, an isotope is an atom, one of the building blocks of nature, and it is an atom with a very specific combination of ingredients in its atomic nucleus, a certain number of protons and neutrons. If it's uranium, it has 92 protons. That's one of the so-called subatomic particles. And depending on what isotope it is, it has varying numbers of neutrons. I won't go and dig into the details of that. You know, I got B- and C in my college physics classes, so it's okay. We can just accept the isotopes for what they are, and I would believe that they exist. Some isotopes that are found in nature are stable indefinitely, like iron 56 is the most common isotope of iron, and iron is ubiquitous. It's found everywhere in nature, and it's an essential, you know, biological micronutrient. We need iron for hemoglobin. Iron 56 is stable indefinitely. It does not undergo radioactive decay. But elements like uranium, the isotopes are all heavy enough. There's too many protons in the nucleus so that they are not stable indefinitely. They undergo this transformation that's called radioactive decay, and we could call the process radioactivity, and we could call the isotopes that do this, we could call them radionuclides or radioisotopes. They mean the same thing. Radioisotope means, you know, one of these guys that undergoes decay, if we could go ahead. This symbolism is used, you know, there's a little bit of scientific notation that comes in here. This is the symbol for the element, that's just a shorthand for uranium. This lower number is it's called the atomic number, it's the number of protons in the nucleus. Often this symbol is written without the 92 because actually if it's uranium it implies that this number is always 92. This upper left number is called the mass number, and that's usually the name of the isotope. So if you say something like uranium-235, you could write 235 like this with the symbol, and then it would be clear what you're talking about. But I'm going to use terms like this. I'll use the symbol U to refer to uranium. Pu is plutonium, and Np is neptunium, and Tc is technetium. Those are 4 elements I'll probably make reference to here today. So the radioisotopes that are heavy like this, they tend to undergo what's called alpha decay. And alpha decay is a process where the nucleus breaks off and spits out at high energy a little chunk of it that's called an alpha particle. It's actually a helium atom. And as a result of this, the atomic number changes, the mass number changes. The process is called atomic decay or alpha decay, but a new isotope of a different element is created. So plutonium-239, I'm sorry, the font is kind of small here. Plutonium-239 undergoes this alpha decay process and becomes uranium-235. And all of these elements up there in the periodic table, uranium, neptunium, plutonium, americium, just about all those isotopes are all alpha emitters. The property of half-life is used to describe the behavior of radioisotopes, and basically what that means is it's the length of time that it takes for half of the stuff to decay away, and the mathematical law that this follows is described by a curve that looks like this. And what the curve kind of says is it never all goes away, but it decays more and more with time. And this is showing an isotope with a half-life of 12.3 years. That would be something called tritium, or radioactive hydrogen. So in 12.3 years, you've got half as much tritium as you started with. And then after 24.6, you've got a quarter. And then after a third half-life, it's an eighth, and then it goes a 16th. You may hear things like, well, plutonium stays around for 250,000 years. That gets repeated in the press often enough. And basically what that is saying is that's waiting 10 half-lives. You will actually have, if you extend this curve out 10 half-lives, about 1/1000th of it left. So if you had 1,000 bags of plutonium, you still have 1 bag left after 250,000 years. If we could go here, what I'm showing is that these isotopes that are heavy and are alpha emitters, those alpha rays, or particles as they are, they don't penetrate very far. You may have heard they've stopped by a piece of paper or skin or something like that. You may have been told, you know, if you get them on your skin, no pasa nada, it's not a big deal or anything like that. The problem with alpha emitters is when you internalize them. If you drink them, if you inhale them, if you ingest them through hand-to-mouth contact, if they're present in your food, if the alpha emitter is getting into your body, that is how it harms you. Because if we could go back 1 slide, 2 slides. We've got this little high-velocity particle just shooting around in your lung tissue. It's like a bowling ball in a china shop, you know, causing internal cellular damage is what that alpha particle is doing. Let's go ahead, 1, 2, 3 slides. There. So uranium is an element of interest, and I think the thing one should be most concerned about is internal exposure. Breathing it, and you have no choice but to breathe. And drinking it. You can do something about your drinking water, that's for sure. Uranium is ubiquitous in nature. It's one of the building blocks of the Earth's crust, even though it's radioactive. Uranium-238 has a half-life of 4.5 billion years, so we still got about a half of it left from when the Earth was formed. But it can be found in soils everywhere, and this is kind of a map that shows you how much to expect. But what I'm showing you here is this is kind of the null hypothesis for uranium. This is what we expect to see anywhere and everywhere. If you could go ahead here. This is a map showing the footprint of the Nevada test site. As you may know, there were nuclear weapons tests done above ground in Nevada in the 50s and the 60s. People used to go out and from the Strip in Las Vegas and go onto the roofs of the hotels, and when a test was announced, they'd go out there and they'd watch the test. You could see it from Las Vegas. Anyway, the footprint of contamination from the Nevada test site and all the other tests. The former Soviet Union was actually responsible for probably 80% of it. But the atomic testing, the distribution of that in the environment, and plutonium comes from that, and neptunium comes from that, and so on, that's pretty well known. So we also know what that null hypothesis looks like, too. We could go ahead. But what I'm doing is trying to see, do the fingerprints match the null hypothesis, or do we have something different? So these isotope or atom ratios, as I call, simply ratios of numbers of atoms, and the mass spectrometer counts atoms, so it measures that pretty directly. It's giving us very distinct information. It's different from how much. It's not really answering the question how much, although we can do that too. It's answering the question, where is it from? Is it from nature because I am accepting the null hypothesis, or is it from somewhere else because I had to reject the null hypothesis? So we can find out about things like enriched uranium and depleted uranium. You heard the term depleted uranium. I've investigated some sites. Aerojet in Jonesboro, Tennessee has a plume of depleted uranium. So does StarMed, is a Superfund site in Concord, Massachusetts. Same thing there. Enriched uranium, I can tell you about a couple other of these besides Piken that are in the continental U.S. Recycled uranium is another term which means uranium recovered from plutonium production reactors. DOE likes to use the term reactor returns, whatever that means. I take from context because they don't ever explain it to you. But what they mean is uranium that has been through a plutonium separation process, and they were reusing the uranium. And when we find neptunium and plutonium, we expect to find them in small amounts. I told you before, my lab does that all the time. I measured a whole tray full of samples from the deep sea near New Zealand, and another tray full of samples from 190 samples from lakes in Iceland. And the idea there is to find out where's 1952, where the nuclear testing debris starts. So we can expect to find these, but in that case it's all from fallout. And the question around here is, well, if we find these guys, are they from this fallout, or is it from the local plant? If we could go ahead here. So if we focus on uranium, there's 4 isotopes that we can measure. The first 3 are found in nature. Uranium-236 is mostly synthetic. Uranium-236, small amounts of it are found in nature, but large amounts of this are present in recycled uranium. So this isotope, 236, is a distinctive fingerprint of stuff from Portsmouth. If you find uranium-236 in the environment around here, that is where it came from, because it doesn't really belong in nature. There's some caveats to that, and on the other hand, if you find this in nature, it's pretty sure to be from a local nuclear site. And so we measure these ratios in our data and test them mathematically. So I'm in a numbers comparison game. I sit in a little windowless room, I feed samples into an instrument, I type up numbers on my calculator or put them in Excel, and I say, aha, and the light bulb comes on. Sometimes the light bulb comes on, sometimes not. I evaluate these ratios to test the null hypothesis, if we could go ahead. So what's different about the uranium that might be in the environment here versus elsewhere is Portsmouth was the site of a gaseous diffusion plant, and this is an old technology for separating and enriching uranium isotopes. This is a cartoon of something called a converter, and the basic idea of this is a porous nickel membrane is inside one of these converters, and a pressure difference. There's a high pressure side and a low pressure side. There's a pressure difference is forcing the uranium hexafluoride molecules through these very small openings. This is all classified. You know, I don't have a security clearance. I can guess how they do this, but I don't know, and I don't care. It doesn't really matter to me, but this is an isotope separation process, and this was done on a vast scale to make ton quantities of various grades of enriched uranium here for, as Pat said, decades. Okay, and so depleted uranium is the leftovers that has a lot of uranium-238 in it, and enriched uranium has more uranium-235 in it. So as this process continues and continues and continues, the isotope composition keeps getting farther and farther away from nature. And these cascade systems, as they're called, they were handling UF6, uranium hexafluoride, as a gas. This is a substance that has a boiling point of 60 degrees centigrade, so it's about 140 Fahrenheit. And so the entire plumbing system, the entire cascade system had to be held at temperatures higher than that. This is why you see those big high tension lines that went from the Madison, Indiana power station to the Piketon plant. Those were supplying the electricity. A lot of the electricity went into the heating and to the pumps, vacuum pumps and compressors used to drive the material through the membrane. So a lot of electricity consumption there. But the system has to be held at high temperatures, so this can only function when the UF6 is in the form of vapor. And this is a very reactive substance. If it leaks out into the atmosphere, and this is a system with miles and miles and miles of plumbing, or it was a system with miles and miles of plumbing, every valve, seal, gasket, everything, all of that stuff, this UF6 leaks out. I know about leaks. I had a cylinder head failure in my car, and coolant goes into the cylinders. That's a fun thing. So, you know, mechanical systems break down and they leak. And so it's easy for me to imagine that over decades and decades, vast amounts of UF6 leaked out into the air. Well, UF6, uranium hexafluoride, reacts, it's very reactive. It reacts chemically with water vapor. And the products are hydrogen fluoride, or when that hits water, it's hydrofluoric acid, kind of a pungent, vinegary smell. HF, hydrofluoric acid, has a very distinct smell. And the other products are uranium compounds with oxygen and fluorine in them that they turn into aerosol. So the gaseous diffusion plant is a giant aerosol making machine. Huge, huge quantities of uranium nanoparticles is what you got from that. And it can't really be helped or stopped, because you can't put together a system that's this big without having leaks and atmospheric releases all the time. All right. So this is just pointing out the business of the recycled uranium. So one path through which this happened is in the late 50s, the government was saying, and this, I understand the time, I wasn't born until 1960, but I understand the zeitgeist of the Cold War era. You know, Khrushchev was banging his shoe on the table at the UN, and Senator McCarthy was looking for communists and so on. We needed to do what we did, you know, as a country with respect to nuclear weapons development, or at least that was the thought at the time. And so we did, you know, the United States did some things like testing atomic weapons on its own soil, and making plutonium and recovering the uranium from these reactors from Hanford, separating it chemically and returning it to the gaseous diffusion plant. The problem that introduced, and this problem exists to this day, is that recycled uranium not only brought uranium-236, which is made in these reactors, that's why I said it's synthetic. Neptunium, plutonium, and technetium come along for the ride. They are present as contaminants in this recycled uranium feed. It's sort of like they built the gaseous diffusion plant. It's like having a car, driving it off the lot, and putting sugar in the gas tank right away. It's basically what it is. These are contaminants. They form fluorides. They behave different chemically, but they are unwanted, and they are going to wind up somewhere. The atoms of these elements are not going to go away. They're going to be somewhere inside the system. They will build up maybe in certain points, in certain places. They'll wind up in the product. They will wind up in the depleted uranium hexafluoride cylinders. I've seen the cylinders out there at the plant. These guys are in there, or they get released into the air. But these were not wanted. But the government made the decision. We got a uranium shortage. They were scraping everything they could find out of the Colorado Plateau. And as somebody who's lived in Arizona and Colorado for many years, I know what the footprint of uranium mining looks like. So they were recycling uranium. We think of recycling as a good thing. In this case, it contaminated the plant. By the way, the French had a gaseous diffusion plant, and they are very proud to say they did not do this same thing. They came to the DOE Waste Management Symposium in 2004, I think, and gave a talk and basically said that. We did not contaminate our gaseous diffusion plant. Whoa. Anyway, if we could have the next slide. Mass spectrometry and what I do, this is a mass spectrum. It's a graphical depiction of numbers of atoms versus mass. And so the data output looks something like this. And I measure how high this is, how high this is, take a ratio. 240 divided by 239 atom ratio. That's a signature of where did the plutonium come from. If it's from atomic testing, it should be 0.18. This is from a place, wonderful chocolate factory called Rocky Flats. This is from a place where they handled plutonium pits for nuclear weapons, and they used what's called weapons-grade plutonium. The ratio is more like 0.05. So if you were to measure these heights in C, it's more like 0.05 than it is like 0.18. By the way, I've detected plutonium in Little Beaver Creek in the sediments, and it is not from nuclear weapons testing fallout, it is from Portsmouth. Okay? All right. So the type of mass spectrometry that I use is called ICP-MS, or inductively coupled plasma mass spectrometry. It's this is very, very mainstream stuff. Every Department of Energy lab, I've visited several of them. I've been to Lawrence Livermore, I've been to Pacific Northwest Labs and Brookhaven National Labs. They all have this type of equipment and do the same thing. I'm using the same type of scientific equipment and principles and ideas, and I read their papers and rely on their papers. So the idea here is that each element produces a series of stick figures representing its isotopes. You can measure stable elements too, but uranium, we want to measure these 4 elements of interest. Here's the building that I work in at NAU. It's a nice mountain town with mountains in the background. I bet you all don't think about Arizona as a place that snows, but we had about 200 inches of snow last year in Flagstaff, and in March we got a pretty good storm, and I got the snowblower out, got the driveway cleared out, and then I was in the lab testing samples. Anyway, we have had several different mass spectrometers there at NAU in the time that I've been affiliated with NAU. So the data output looks something like this. Here's a mass spectrum. Here's 3 peaks that show up. This is naturally occurring uranium. This is what you might have in a typical drinking water sample. It's well below the drinking water standard of 30 micrograms per liter, but there's a big uranium-238 peak, a smaller 235, a very small 234 peak. Not really anything Here, this is a logarithmic scale, so that's misleading. You have to think in terms of each notch here is a power of 10 instead of it's a linear scale. We go to the next one. Here's a different flavor of uranium. This is enriched uranium. This is actually fairly highly enriched uranium. It's coming from the Nuclear Fuel Services facility in Irwin, Tennessee. This is being discharged into the Nolichucky River, and you can see just from looking at this versus the last spectrum, something's way different here. There's a lot more 235, there's a lot more 234, and there's quite a bit of 236 that shows up. This is all uranium that has had that recycled uranium blended in, all that stuff handled at NFS to make fuel. Navy fuel is what they make. A lot of that was enriched at Portsmouth, so it's the same material. If we could go ahead here's an example of what some of these data look like. There's another fuel fabrication facility in Apollo, Pennsylvania. It's in the hills east of Pittsburgh, about 40 miles. And I took a cluster of samples here near Apollo, and it might be a little bit difficult to see, but here's the 235-238 ratio. Down at about 0.0072 is the magic. This is what we expect from nature. And what I'm showing you here is if we go far away from the Apollo facility, the uranium is exhibiting the same isotope composition that it should have from nature. And in other words, these guys here, we are not rejecting the null hypothesis. We're saying the null hypothesis is good. These points here, though, the 235-238 ratio is systematically higher. There is a presence of some enriched uranium in those samples, and the ratios go much, much, much higher. And so what we're seeing from these data is that the footprint of how far this contamination goes is about 2 kilometers. So somewhere around, where all those cluster of yellow points, a radius of about 2 kilometers is about the zone of effect of this particular facility. It's certainly contaminated there, but it doesn't go very far. Irwin is along the Nolichucky River, as I showed you. It drains discharge of stuff from an NPDES outfall as well as groundwater discharge into the river has caused contamination to go downstream. Next slide. And we found where the river ends is about 95 river miles downstream. It ends in what's called Douglas Lake, a large TVA reservoir. I went and did some sediment cores from that area, and this is what you see. There's some lenses of enriched uranium in the Nolichucky River terminus. So the contamination has flowed downriver 95 miles from that place. All right, well, that's some things that I did in the past. In 2018, I had recently sort of retired, although I intended on beginning a post-career phase of life. And I was thinking about what to do, and I was honestly beating myself up because my mother and father had lived in Ohio for 40 years. And my family, myself, had lived in Ohio for 5 years. I lived in Lake County, Ohio, up in the Cleveland Snowbelt. And I taught at John Carroll University. But all that time that I lived in Ohio and all those years, I thought to myself, I don't really know anything about Piketon. I've never been down there, and I'm very familiar with the cultural divide that kind of exists in Ohio. If you ask people up in Cuyahoga or Lake County or places like that about things down here, what do they do down in Piketon? What's this A plant about? Nobody has a clue. And I'm guilty of that same thing too. So in 2018, I said, I'm going to learn about this place. I did some reading. I had the occasion to make a trip down to Ohio, and so I snuck down to Pike County, and I took some samples. I don't think anybody saw me. Maybe somebody did, but I don't think anybody saw me. There's my little rental car, and I'm over by Little Beaver Creek somewhere. And so I took some water samples and so on. Go ahead. And it just was shocking to find contamination, plutonium in the Little Beaver Creek sediments, neptunium, enriched uranium in water and in soil. I was pretty shocked. So I got into contact, I contacted several community members, and I began working with Lamersons, Elizabeth and Josh Lamerson. And that culminated, I worked with a colleague at NAU, Scott Sechaney, in the early stages of this project. And he and I co-authored this report, and we presented this to the community on April 27th, 2019. So in the intervening time, I have continued to do things. But some of the things that we presented on April 27th, and you can go to this YouTube, and I want to give a thank you to Bobby Vaughn, who's over here with one of the video cameras. Bobby made this recording and posted it on YouTube, and I presented by telephone. This was in the pre-Zoom days. I presented by telephone some of our findings. And at that same meeting, I heard some things from DOE that were quite interesting. Because to put this in context, this was right after the community had learned of the neptunium detection at Zahns Corner School. So the meeting was held in response to that. And Elizabeth Lamerson and Matt Brewster made arrangements for me to talk at this meeting because my report, my study of several months with Scott was just about ready now. We were ready to go tell the community what we had found. So what we found is that the neptunium at Zahns Corner has to be just about definitively from Portsmouth, and it's not from global fallout. Department of Energy, Jeremy Davis, I heard him on tape. It's on tape here. He made a false allegation that the neptunium at Zahns Corner was from nuclear weapons testing. Jeremy, my friend, I think you're out of your league on making this statement, to put it lightly. The neptunium that was found at the Zahns Corner school by DOE's own air monitors. I found neptunium in many other places around this site. It's all from recycled uranium. It was introduced into Portsmouth starting in the 1950s. And I found it in water, it's found in soil, ambient air, dust, etc. We could go ahead to the next slide. Despite that, one back.
This is the next one.
This is the next one. Okay. All right. Despite all the statements by the DOE, this is the DOE's own data. This is a Lawrence Livermore National Labs study called the Moody Report. And here's a table showing these are all the isotopes that are present there. There's neptunium-237 on the list. Here's a report that's done by Bechtel for DOE, Recycled Uranium Mass Balance Project. And it looks like my graph here didn't come in, but they have a graph in there that shows the history of when the neptunium-237 came into the gaseous diffusion plant. And then if we can go to the next slide there. This is May 6, 2019. This is after the Zahns Corner School, and this is signed by Jeffrey Bettinger of DOE. He's basically saying the source of the detections is not known, referring to the neptunium at Zahns Corner School. The source of the detections is not known. Well, I know what the source of those detections is, and I think everybody that looks at the logic can see that too. Go ahead. So I wrote Matt Brewster, I got to know him, the Pike County Health Commissioner. I wrote him an analysis of the situation, and I made this statement: to a reasonable degree of scientific certainty, the implied source is fugitive dust from the Ports facility. It's not from nuclear weapons testing fallout. So what's the basis for that? The problem is that there's a null hypothesis for neptunium. How much neptunium-237 can be expected and how much relative to plutonium-239 can be expected? And I'm relying on DOE's own papers. The guy that wrote the seminal papers on that topic worked at Pacific Northwest Labs, funded by DOE. So I rely on their own data, and that's what it shows. So what was DOE's response? Portsmouth Paducah Project Office hired Savannah River National Labs, I'll just put it in simple terms, to go after me. All right? They went after me. And thanks to the Freedom of Information Act, and my hat is again off to Bobby Vaughn for giving me some stuff under the Freedom of Information Act, I got to read some of their emails. Here's a person named Leo who works for headquarters. I don't really know who he is, but here's some Savannah River National Labs people. Mahidi is the lab director. Here's somebody named Dennis Jackson who is talking about, they're trying to discuss in their emails, who is this Elizabeth Lamerson and what are her credentials. So DOE and their contractors are in the business of investigating local residents. Okay? If we could go ahead. Here's some more, let's pause at this slide for a minute. Anne is referring to Anne-Marie White. Anne was soliciting information. What are we going to do about this? What are we going to do about this? She wound up promising the community this independent third-party study, which you know about as well. But here's some things from these FOIA emails. Fran Dickens, senior health physicist, radiological engineer, and certified health physicist, referring to Lamerson's samples, says, I don't think the samples were handled correctly and there may have been cross-contamination. I beg your pardon. I beg your pardon, Fran. I beg your pardon. I highly doubt the dust samples and the soil samples from the school and home has neptunium, plutonium contamination. Well, you can argue balls and strikes with me with the mass spectrometry results. Let's have it. Let's have it. Bring it on. And then here's Dennis Jackson talking about Elizabeth Lamerson. Oh, this is what I found out from her LinkedIn profile. You know, Elizabeth is a community member, is not getting paid to do this. Going after me is one thing, but going after a community member is something different. I'm sorry, that is not right in my book. We can go ahead. Lamerson's, just to point this out, Lamerson's use low-blank baby wipes. We talked about this. You go to a dollar store and you get these wiping cloths. They have very, very, very low intrinsic uranium concentrations. There's no plutonium detected in them at all. Wipe these surfaces. It's the way to collect evidentiary samples. On the other hand, what did DOE do? They sent Savannah River over there with these glass fiber wipes. I got splits of these from Matt Brewster, and I found that they contain 30 nanograms of naturally occurring uranium. So they're using contaminated wipes. It's sort of like we're trying not to detect something is how this really looks. And they sample 100 square centimeters as their defined protocol. And yes, they are trying to do something different. They're trying to see, are there any acute radiological hazards? Well, that is not the point of what needs to be done at all. So I'll go with the mom with baby wipes and not what Savannah River does, okay? So here's Carol Eddie Dillick of Savannah River National Laboratory, member of the technical staff. Here's quoting from her emails, if you can, and referring to me. Could you put together a short summary that describes how his method uses a fringe science approach? So, among friends, I am, as a term of endearment, known as the fringe science guy. And you're welcome to call me the fringe science guy because she already did. But let's just look. Here, Google Scholar. You can take your phone out right now, scholar.google.com. Type in my last name and type in plutonium, and you can see what I published. This is an older view graph, 136 citations, 124, 101 here. Some pretty good papers. And, well, you can go and see what Fran has done, too. And you can judge for yourself who has credentials. I'll just flip through these because I'm taking up a lot of time. I published this in 2004, plutonium in sediments for dating purposes. We'll go to the next one. Fingerprinting plutonium in Poland. There's plutonium from Chernobyl. Here I am in 2005 with much less gray hair. And in Krakow, Poland. This is a review article from 2008. And one more. And one more. This is recent from last year, published in Nature Scientific Reports, and this is my plutonium data set as the basis of this paper. So I think it's fair to say I'm not trying to brag, I'm just trying to point out facts that I might have some knowledge and some skills, and I'm not doing fringe science if I'm getting published in Nature Scientific Reports. Anyway, I did some work for Matt Brewster in looking at uranium isotopes in the samples that Savannah River collected at Zons Corner School. We could go ahead from there. And red means we're rejecting the null hypothesis. So all of these red data points, these are some of Lamerson's white samples from Zons Corner School. These are some of DOE's samples that we could still find the enriched uranium despite the 30 nanograms in the glass fiber. But I sent Matt a report that detailed all this in June of 2019. And I want to give credit to Elizabeth Lamerson, not only for taking a lot of samples from those places, but she's been working with Scioto and Seal townships and running an air monitor, including another one on her own property. So this is a high-volume air monitor, and she sends me these air monitoring filter sections, and so I punch a subsection of this, and then I do chemistry on this and use the mass spectrometer to see what's happening. If we go to the next slide, here's some results I'm going to show you from that air monitoring program. And so this is a time series that starts about 2019, ends mid-2021, and so it actually ends shortly before they began with the open air demolition. But it's quite interesting what you see. So if uranium is from nature, it should all be down here by this dotted line. But it's not. So what this means is that during this 2019 time period, they're emitting enriched uranium into the air. It's being detected. This is Lamerson's monitor at their property. It's being detected in their plant. But it's interesting to see what happened when COVID starts, March, April 2020, somewhere in there. Plant activities start. Everybody got sent home. All activities stopped. No more D&D work taking place on the plant site. Look at what the uranium does. It returns to naturally occurring values. The uranium in the air is almost all from nature at that point in time. And that's during the first 3 months of COVID, and then about July, August, it picks up again. I call this the so-called COVID hiatus, and I want to give a shout out to Dwayne Pullman too for his wonderful coverage from Cincinnati Channel 12, and we talked about the COVID hiatus. You can go and find that footage on their website. We also analyzed filter sections. We find that during the COVID hiatus, the uranium concentrations in the air were lower. There was no detectable neptunium-237 in the air during the COVID hiatus. Before COVID hiatus and after COVID hiatus, the uranium concentrations were higher. The enriched uranium was definitely present. Well, should we hold the questions until the end, or should we?
Probably, yeah.
Probably.
After the speakers are finished, we'll have the questions.
Okay. All right, there we were. Okay, we can go ahead to the next slide beyond there. There we go. Okay. All right. This is just showing, I'm just making the point that the neptunium is indeed present. The ion count data, I look at numbers on the mass spectrometer. Here neptunium is present, here it's not. Here's before the COVID hiatus, here's during the COVID hiatus. End of story. I call balls and strikes, you know. It's like when I went with my car with the cylinder head problem. I went into the shop and they said, well, you know, here's the picture of the coolant leaking into your cylinders. It's tough to deny. It's the same deal here. I'm just the bearer of the bad news, just like the shop was on my cylinder head gasket problem. Anyway, if we go ahead here. So in mid-2021, DOE started with the open air demolition of the X326 building. This is an in-progress picture. If you go ahead one more slide. This is a video that maybe some of you have seen that Elizabeth sent me from a community member. Here's the beginning of the open air demolition. There's a water cannon shooting debris shooting water at the debris, and there's a tarp up here that's flapping around. If you click on that, I think it will play. You can see the tarp flapping around in the breeze. You know, that's your open air demolition. So I'm not showing any data from what happens after 2021, but I'm just going to ask you the question: what do you think happens? What do you think happens after they start the open air demolition? That's all I'm going to say on that. If we could go ahead now. So what was in the air during the D&D? This is a very interesting report. This is also a DOE-funded study. I call this the Spent Trap Media Report. During the time frame about 2013 to 2016, DOE was cleaning out the cascade. They used this process called LT-LT. And they would seal up sections of the gaseous diffusion plant plumbing. They would introduce gases like bromine trifluoride and chlorine trifluoride, all kinds of chemical witchcraft. And the idea is to get those solid deposits back into gas form so they can draw them out and hopefully collect and reuse them. Well, they put traps on this system to scrub the stuff that's vented into the atmosphere. This is describing the composition of that stuff that was being vented into the atmosphere, or hopefully trapped by the trap. And you can find this report. It's a public domain document. If you go ahead one more slide. This is a table of compositions. This stuff was so radioactive that it had to be sent to the Nevada Nuclear Security Site, it's called. It got sent out to Nevada. This did not go into the on-site waste disposal facility. This got sent out to Nevada because of its high levels of radioactivity. Well, look at all the stuff that's in the list. I report to you that this is what was blowing around in the air during that time period. The time period here that was really bad was about 2013 to 2016. If we could go ahead, another slide. This, you're not going to be able to see all the details here, but I'll tell you what this is showing. I went to DOE's data system called Pegasus. P-E-G-A-S-I-S. Pegasus is DOE's online data system, which you can download all of their public domain data. I went there and I looked at the technetium-99 data from about the 2010 to 2020 time frame. I downloaded all that data and I looked at individual monitors. And what's astounding about this is here's a monitor A37 Otway, far southwest of the plant. The levels of Tech-99 found in the air in Otway are practically the same as they were at all of these close-by monitors. And what that is saying is that this stuff went out as a gas and it went far and wide. During this LT-LT cleanout time, that stuff contaminated probably all of Pike County and part of northern Scioto County and who knows where. We don't know. We do not have a good handle on how far it went. If we can go ahead. So this is the Pegasus system. I urge you to go there and take a look yourself. Another thing that I've been interested in is the substance neptunium. Neptunium as a chemical element is very long-lived. It has a 2 million year half-life, but it has some water solubility to it. It forms this species, this chemical form that likes to go into solution in water. And I started looking at Pegasus and I found some of DOE's data. There's a plume of neptunium contamination by the former X701 building. I downloaded some of DOE's data and they report a detect of 1.48 picocuries per liter. That's actually quite high. But they have some interesting things that they do with these data points. I think that these are detects that they are calling non-detects because they don't want them to be detects. Because they don't want to be able to they do not want to have to say that this contamination is there and there is a plume. If they say, oh, it's only this one point, then they can say, oh, well, it's a one-off, it's not a plume. Okay? So this is discharging from this area of the site, going into Little Beaver Creek and into the Scioto River. If we could go ahead. This is just looking at, here's the detect, and I have my suspicions. Look at this packet of data and this one, and look at the blue points. These are all non-detects according to Pegasus. I'm not so sure about that, my friend. We could go ahead. Same thing. I told Pike County here, you ought to go to Ohio EPA and US EPA. Tell them to have an enforceable standard of 0.15 picocuries per liter. So Ohio EPA or US EPA, if you're listening, why have you not set a standard of 0.15 picocuries per liter for neptunium in water? You have it as a problem on this site. Why aren't you setting that as a standard? Where's that number coming from? Well, DOE stipulated to that in the legacy management agreement at Rocky Flats. For plutonium, 0.15 picocuries per liter is the standard. We can go ahead. I found some other interesting things about neptunium. Vine has this document, and Bobby Vaughn has this document, and they've got this from both those guys. And the date on this is December 30th, 1976. And if you look at this, it's talking about, we got a serious neptunium problem on our plant and it's leaking into the creek. So they knew about this in 1976, and in 2019 they're telling you it's coming from global fallout. Okay? Think about it. Well, what's DOE's response been? This is an old slide, so I haven't updated. This is from last year, but once I opened my mouth about neptunium in water, DOE stopped posting any data on Pegasus on neptunium. Go ahead to the next slide. On the other hand, the Department of Energy seems to know quite a lot about neptunium, and they spend quite a lot of money studying it. Here's a paper. Brian Powell is at Clemson University. He basically makes his living off of DOE funding, studying neptunium, works with Savannah River. I believe Peruski is now at Oak Ridge National Labs. But the long and short of this is that neptunium has a propensity to go into solution and to migrate in water. That is the bottom line of this paper. DOE spends millions of dollars studying that, and they've known about neptunium in the water at Portsmouth since the 1970s. You know, I looked at that memo and I said, I was an undergraduate student. I was a freshman in college when they wrote that memo. That's how long ago it was. Did DOE ever come to you and talk about neptunium in your water? I don't think so. Go ahead. So we've been looking, and so you may know where Little Beaver Creek is, and here's Big Beaver Creek, and then it goes this way towards the Scioto River. I've done some sampling in this area when I first came to Piketon, and I've now analyzed 2 sets of samples, one from Vinacali and one from Elizabeth Lamerson, 2 different people at 2 different points of time. We've found neptunium in it, and usually the concentrations are so low that you have to work at it to do work, but I was able to use 20 milliliters of water in one of the samples that Vina took is enough volume to detect neptunium. That's shocking. That is shocking. Anyway, neptunium is present in these off-site waters near Portsmouth, and it's, if we could go ahead. One of the things that's worrisome here is it's possible that neptunium is going up into plants and into the food chain. Okay? This is a very old report, and it's talking about translocation of neptunium and a bunch of other things by a wheat crop. If we go ahead to the next slide here, the long and short of it is neptunium has a much greater propensity than does plutonium and these other ones to go into plants. So I would worry about this. Well, what about Tech-99? Well, Tech-99 is even worse. Tech-99 goes into plants, and I think you can expect to find it everywhere around here in the water, in the plants, in the animals, and in human tissues. All right, if we could go ahead. So, a couple more stories to share here. I know I'm pretty long-winded, and I hope you've found it worthwhile to listen. But I want to tell you about some recent results from Charles or Chick I I acquired a sample of dust from Chick Lawson's attic that Chick and Dwayne Coleman sampled. This was in one of the Fallout television episodes. And I analyzed this at NAU. And long and short of it is, a very simple declarative sentence. Attic dust collected from your residence contains enriched uranium. The attic dust contains the isotope uranium-236. That's the synthetic one that's specific to Portsmouth. We also found neptunium, and no, the neptunium's not from nuclear weapons testing. So there's definitive evidence of nuclear fallout, not from weapons tests, but from Portsmouth. So here's a pitch for going to Local 12's website and looking at some of that footage. And here's some results from that report. Here's a ratio of atoms, neptunium over plutonium. If this was from global fallout, that number would be about 0.47. Instead, it's about 8 to 10. No can be, but that is global fallout. Neptunium in Lucasville. Think about Lucasville is about 10, 11 miles south of here. This plume is pretty big, and I don't think we have a good handle on how far it goes yet. And we can see in Chick Lawson's attic dust that it's mixing between naturally occurring uranium is down here, and there are different flavors of enriched uranium found in different wipes collected from his attic dust. And Little Beaver Creek sediment also has enriched uranium in it. It's a little bit different, and so on. And we also found this graph here is kind of showing, well, if it's from atomic testing, it ought to be in here. If it's from Portsmouth, it ought to be here. And that's where it is. Okay, one more thing I can tell you about here is I've also worked with Jeff Walburn, who's here today, and I thank Jeff for his collaboration. Jeff sent me some hats and a balaclava that he wore on the job. Jeff was a security guard at the former gaseous diffusion plant. And so these pieces of fabric that he wore on the job for hundreds and thousands of hours, they're kind of acting like a dosimeter in a way. They're soaking up gases and particles from the air which they come into contact with. Think of it as it's like going to the bowling alley in the old days when everybody smoked at the bowling alley, and you'd come home and you'd smell like that smoke. It's on your clothes, it's on your person. So these objects contain very high levels of enriched uranium. And so I guess that means that people who were in the building, working in the building, were breathing that. This is direct proof of occupational exposure. All right, so some of the take-home messages that I have is uranium isotopes are kind of like a truth serum. Not everybody likes to hear the news that the contamination exists. I know of people that are upset that I'm not finding contamination. I don't know what to say, but if it's not there, it's not there. I'm using the truth serum. I'm not in the business of doing risk assessment and assessing radiological hazards. I am interested in following trails of breadcrumbs, seeing where the contamination comes from. Where does it go? I focus on the questions that are more like, does this come from there? And I would say that pretty much anywhere around here, maybe within 10 miles, I don't know how far, but pretty much anywhere around here, we can expect this contamination to be present everywhere in the environment, in the ambient environment, off-site, near the facility. I don't have a good understanding now how far it goes, but it's in Lucasville and it's in Otway. It goes that far at least, and it's certainly in many locations right around here. So the geographic extent is not well known. Okay, we can go ahead. So what the community can do, I would say you can't really solve this problem. All you can do is really have an intelligent response to it, not a solution. But an intelligence response would be really to take the matter into your own hands. The DOE and all of its contractors and the state, US EPA, Ohio EPA, all of those agencies, all the elected officials are not going to do a thing to help you. They are not on your side in this quest here. You need to assume responsibility, my friends in the community. You need to you're responsible. If you want to live here, if you do live here, you need to understand and monitor your own environment. You need to assume that responsibility. Do not count on them. I think the record of decades shows we do not want to count on those people. You should work with your neighbors, assume responsibility, limit your exposure, mitigate hazards that you can identify. I work, and I will help you in these things. I work with affected communities to assist you in understanding your environment. I help people with environmental monitoring through a citizen science-based approach. So, lots of ways for citizens to monitor their own environment. Fugitive dust sampling is very easy. You just wipe with a baby wipe on a smooth surface. There's your sample. I incinerate it and look for the breadcrumbs. It's as easy as that. We can find it. And all of these places are all releasing lots of particles into the air. Okay, we'll go ahead. This is a homemade high-volume air monitor that I'm working with. I have one of these set up in a couple of locations in the U.S. This is from Harbor Freight. It's about $89. And it plugs into AC power. It draws 1,700 CFM through it, and you put a piece of filter on the inlet side of this, and you collect the material. There's your air sample. We go ahead. This is another technology that I'm working on that's battery powered. I got a pretty good finger wag from my wife, and she said, you better take that off and get your own blankety blank leaf blower. Do not use my leaf blower. But the idea here is this is a portable air monitor. The N95 mask is serving as the filter. This is the inlet. It's blowing out that way, and on one of these 4 amp hour batteries, it'll run about 20 minutes, something like that. But you can walk around anywhere and collect air samples that way. This is 1 week on the Harbor Freight air monitor, so I take that and analyze that material. And another thing, if you're interested in water contamination, there probably are little mollusks that have calcium carbonate shells that grow in the Scioto River. Somebody out there might be interested in going and collecting those. Their skeletons will contain whatever uranium was in the water. They sample. They're biomonitors of the contamination. This is from the Nolichucky River. And at NAU, we are just in the business now with a new mass spectrometer that's going to do better things for us. I'm looking at it as I have 10 plus years of future technological viability with this instrument. It's now installed. I'm learning how to use it. To date, we have not made any Tech 99 measurements, but it's coming. It's coming. And this is my email address. I want to warn you that emails sent to NAU are subject to the Arizona Open Records Act. And so what you should do is send me your name and your phone number. If you want to contact me about collaboration, send me your name and your phone number, and I will call you, and we will get a dialogue going on Signal or something like that, because this email is discoverable. I just want to end by thanking a lot of people, some of whom are here today. I want to thank Vian Colley and Michael Ballard, Bobby Wan, Terry Lodge, Chick Lawson, Jeff Walburn, Steve Lettingham, Dwayne Pullman, and all of the members of the Ohio Nuclear Free Network have contributed greatly to this. One more slide, and I want to thank my hosts at NAU and the Ingram Research team that I collaborate with. There's a little room where I call the balls and strikes. So thank you for listening, and we'll go, I guess, to the next talk. So the first question reads, your research begs the questions. 1, how far in radius from the port site would you need to go to get results consistent with the null hypothesis? And I don't have the answer to that at this time. I can say that I have identified the contamination in a lot of places that are within 4, 5, 6 miles of the plant, but we have also found it in Lucasville, and that's more than 10-ish miles or so from the plants to the south. And we've also seen in DOE's own air monitoring data from Otway, which is southwest of the plant, more than 10 miles.
It's 14.
14. We have seen the DOE's own data shows that contamination is there. So there's some sketchy information that answers this question that's basically just saying it's pretty large. The footprint, the radius is pretty large. I can tell you one of the things that I'm interested in doing is sampling dust from people's attics, going into attics with baby wipes and wiping dust that's collected on rafters and trusses and on sheet metal and things like that, that reflects stuff that's settled out of the air in previous decades. And I think the answer is we got to go really far away, maybe all the way to Cincinnati and all the way to Pittsburgh and up to Columbus and down to the Tennessee border and work our way back towards the plant. The second part of this question is, do you ever have results that confirm contamination levels are below your detection limits of your instrumentation? Well, for uranium, pretty much we're detecting uranium in every sample. Detection limit is rarely a concern. However, we do find plenty of samples where the ratios are consistent with the null hypothesis, and therefore I conclude, well, there doesn't appear to be any Portsmouth-related contamination in this location. And I have found samples from this area that do not exhibit enriched uranium, and there's usually an explanation for that. You know, it's fill dirt that was brought in from somewhere else, or it's soil that was from 3 feet deep that the atmospheric deposition has not penetrated down to. Let's see. The next question is reading, is it true that DOE has given management immunity from the prosecution? Is it true that DOE will spend our tax dollars defending previous contractors? That is a question that might be better suited for Terry Lodge, but I just point out that the Price-Anderson Act is a piece of federal legislation that indemnifies the nuclear contractors from a lot of liability. It puts limits on their liability. I am not an attorney, and I'm not an expert in that. Terry, do you want to add any comment to that thread?
Yeah, I will.
Okay.
Go ahead.
Okay. So the next question is, when was the largest release of radiation? 60s, 70s, 80s, 90s, or 2000s? I don't have a good answer for that. I think it occurred continuously. There's bits and pieces that show this happened then and this happened then. I think during the previous decade, from about 2013 to 2016, as I mentioned, from DOE's own air monitoring data, there were massive emissions into the air of Tech 99 and so forth. And was it more from enrichment process or the massive storage from around the country? I'm not sure what the massive storage is around the country, but I think a lot of it is just gases leaking out from the cascade, and it could also be, you know, stored cylinders of depleted uranium hexafluoride are also leaking out into the air. The final question is, where should we move that is safe? Well, that's another interesting question, and I think the answer to that is there are probably some type of environmental hazards anywhere you go to on this planet. And I think the person who wants to do appropriate due diligence should, you know, kind of investigate and understand their own environment that they live in. That's the best that I can say. Here's another question. How do your tests and samples compared with DOE samples? Do DOEs have tests for this area? I think that one ought to ask DOE that the community ought to be demanding more from them, because I'm the guy that lives in Arizona. I am not the perpetrator of this problem. DOE, you are the people that are responsible. You ought to answer the question. But how do my wipe samples compare? Well, we managed to find enriched uranium in Savannah River National Laboratory's wipe samples from Zahns Corner School, and also found enriched uranium using the wipe samples that Ms. Lamerson collected with baby wipes. So that to me is about as comparable as you can get. So There's one more question here for me. Who is to blame for the X-326 fire? I do not have any specific knowledge of what that's referring to. So that's it for the formal questions that I have.